Thank you. So in the next few minutes, I want to present a study that we did together with the World Bank, with Nick Jones, into predicting OSM completeness for disaster management by means of remote sensing in the case study of small island states. And as you all know, in the last few decades, there's been an increase in the frequency and severity of natural disasters, especially those related to extreme weather events and floods, with around 60,000 people killed every year due to natural disasters. But the distribution and the impact of these events is not equal, and low-income countries and developing countries are especially vulnerable to these events. Within these countries, small island developing states are especially vulnerable. This is a group of 39 countries with 65 million people, where 1/3 of the population lives in less than 5 meters below sea level, meaning that they are more vulnerable to sea level rise. In addition, the annual cost of the disasters in relation to GDP is much higher than that of larger countries, 4 times of larger countries. And these are just 2 examples of the devastating results of natural disasters. In the case of Haiti, the 2010 magnitude 7 earthquake, which killed close to 250,000 people, and Hurricane Matthew in 2016, which also caused a lot of destruction and many casualties. So during a disaster, there is a need for an effective and efficient disaster management and disaster relief. And the key for an effective disaster management is accurate and up-to-date geospatial data, which can be used in the full life cycle of the disaster event, from mitigation through preparing to the event, responding to it, and recovering from it. And this data is needed for everything from forecasting and modeling the impacts, identifying locations of critical infrastructure, or doing damage assessment. And traditional methods to collect this data are by means of remote sensing. For example, satellite data, aerial imagery, UAV data, mobile GPS devices. And this data is available by different agencies, whether private or public. On the other hand, in the last few years, in the last 10 years, we see another source of geospatial data that can also be used for disaster management, called VGI, Volunteer Geographical Information, where geographical information, geospatial data, is contributed by volunteers by different means. And this trend was recognized in 2006 when Time magazine chose you as the person of the year to recognize your contribution to today's 2006 information age. One example of VGA, or one of the most important examples of VGA, is OpenStreetMap, which is a platform for collection, management, and dissemination of VGI data. It was created in 2004, and contributors contribute geospatial data by different means, aerial imagery, GPS tracks, and others. There are more than 3 million changes every day to this database. However, this database is not complete, and we talked about it in the panel. Typically, or generally speaking, developed countries are more mapped than developing countries, and within countries, urban areas and highly populated areas are more mapped than rural areas or villages. So the question is, how do we identify which areas have not been mapped yet? And traditional methods to estimate the completeness of OSM basically rely on comparison between OSM and other vector data sets. So for example, we can compare the completeness with cadastral data. We can compare the completeness with vector data of building footprints or from different resources. Problem is that this reference data is not always available, especially in the case of developing countries. So the approach that we proposed in this study is to rely on remote sensing measures to estimate or predict the coverage of OSM building footprints. How do we do that? We look at different characteristics of the land, of the surface. For example, we rely on Sentinel-2 derived spectral indices, for example, to map vegetation, for example, to map built-up land cover. All the data sets that we are using here are free and publicly available related to what we talked in the panel. We also look at the texture of the surface, whether it's smooth or not, which can also tell us something about the buildings, the structures, vegetation. We also look at the slope, topography. We look at forest cover, how much of an area is covered with forest. Importantly, we also use nighttime light data as another measure because we estimate that those areas that are covered or should be covered with OSM emit more light than those areas that are not populated. We also rely on remotely sensed derived products of built-up land cover, and we relied on two data sets. One is GUF, the Global Urban Footprint, and the other one is the WSF, the World Settlement Footprint, which is available in resolution of 10 to 12 meters. And in addition, we added some additional features related to the transportation network also, which we extracted from OSM, the roads, road length, and junctions. So the case study was the small island states, Haiti, Dominica, and St. Lucia. But in this talk, I will just focus on one of them, Haiti, which has a population of close to 11 million people. Over 6 million people live below the poverty line, and since 1998, the country was hit by at least 10 hurricanes. So it is highly vulnerable to natural disasters. In addition, it is an interesting case study because while many areas in Haiti are mapped, other areas have not been mapped yet. So what you see here on these maps, in yellow is the existing building footprints in the database compared to a high resolution base map. So how do we do this analysis? How do we determine automatically that these areas have not been mapped yet? We divided the country or each of the countries into a grid cell. For each grid cell, we recorded the total area of the existing OSM building footprints and the number of OSM building footprints. This is what we want to predict. We want to identify those cells that do not have enough OSM building footprints. How do we do that? How do we predict? We predict with all these measures, with all these predictors that I showed you previously. So we are looking at the nighttime lights, we are looking at the amount of vegetation, the amount of built-up land cover with different indices, the amount of forest cover, the amount of built-up land cover according to the remotely sensed derived products, and others. So these are the features that we will use to train and then to predict which areas have not been mapped yet. How do we do that? So first of all, we created a data set of ground truth, 835 grid cells, which we assessed that they are at least 75% complete in terms of mapping, because then we can rely on this data set to estimate or to teach the classifier what are the characteristics of mapped areas. So first of all, we found that there is a significant and high correlation between the total area of OSM building footprints and the different remotely sensed derived indices, whether it's nighttime light data, UI, which is an index for built-up land cover, and DVI, which is an index for vegetation. When we created a model fit with a stepwise regression analysis, we saw that together all these predictors explain up to 82% of the variation in OSM building footprint area. This table just shows the contribution of different types, different categories of data. Just by looking at GUF and WSF, we can explain 66% of the variation. But with the addition of other data, for example, nighttime lights and other remotely sensed derived products and the OSM transportation corridors, we can explain up to 82% of the variation. We also did a random forest regression model, which showed this validation was done with 5-fold cross-validation. We can explain 89% of the variation in OSM building footprint area. And also, as we increase the number of trees in the random forest up to 64%, the accuracy improved, and then it remained stable. But at the end of the day, we don't just want to see these analysis. We want to actually identify those cells that have not been mapped. So we trained this random forest with the 835 grid cells, and then we applied the random forest to predict the coverage, the total area of OSM building footprint in the entire country. So what you see here on the map is the total area that was predicted by the classifier to be, by the model, to be covered with OSM building footprints. And this is when you zoom in, you can see these cells, the pink areas, the purple areas show areas where we predict they will be, should have a lot of building footprints. And this is just overlaid with the existing building footprints. And what you can see here is that we can actually detect those areas, those cells that have not been mapped yet. We did it by calculating the ratio between the predicted area and the actual area of OSM building footprint. So these areas show cells where we don't have enough existing building footprints, but the classifier predicted as having a lot of building footprints. So, to summarize, with the increased frequency and severity of natural disasters, we need accurate and timely geospatial data for an efficient disaster management. OSM dataset provides this data which can be used to, for example, prioritize search and rescue operations during these disasters. Traditional methods that estimate OSM completeness rely primarily on official vector data sets. Here, we propose to use this methodology to predict its coverage by means of remotely sensed data. And as you saw, all of the data sets that we're using are free and publicly available. Moving forward, we want to extend this study by, first of all, analyzing other contexts, not just small developing countries, but also Nepal, India, Bangladesh. And we want to evaluate other predictors to the model, for example, world pop data and other data sets. All the results of this study were published 2 weeks ago in remote sensing, and you are welcome to check it out. So thank you.